So welcome to the pre-recording of lecture 20 of MCS 572. So this lecture is on the data parallelism in matrix multiplication. In a way, it's also an introduction again to the compute unified device architecture of NVIDIA. Although towards the very end, I go towards Julia. So Julia has the CUDA .jl package, but also has other packages for Intel GPUs, for which it uses one API, for Macs, for which it uses Metal, and then there are also the GPUs for AMD. So there are the AMD GPU packages. So it is possible to program GPUs with the same code using Julia, but I will go into that at the very end. So what Julia does, it gives a very high-level introduction to the subject. But in this course, we are interested in understanding an insight. C is therefore an extremely good language. One can say, well, of course, there is the two-language problem, but if you are capable of C and C++, then and really wanting to be close to the hardware, then C is perfectly fine. Speaking of performance, so I will indicate how to use a tool, perf, to do a performance analysis. So even already for the very plain code that we will consider here, we will show that the code itself is actually already quite performant. Okay, so this is lecture number 20 in the course. However, it's the fifth lecture on GPU acceleration. So in a way, it's on a very specific topic in the course. And I will try also to again repeat the essence of GPU acceleration. Okay, so what do we need? We need that we can compute on data independently. So there is this data independency that characterizes the graphics processing unit. So that leads also to the data parallelism. So one of the key illustrations is the multiplication of two matrices. So many problems in scientific computing can be reduced to matrix multiplication. So what this boils down to is making many inner products. So here you see the formula for the inner product. So the ijth element of the in the product of matrix A and B consists of making the inner product of the ith row of the first matrix A with the jth column of the second matrix B. So we see one loop. So if everything turns out right, then a computation which is cubic in the dimensions, if n, m, and p are all equal to n, then this requires n to the power 3, so cubic in the dimension. But if everything turns out right, then this can turn into a linear computation. So this is quite amazing. So the most important part for which this can happen is that all the data elements can be computed independently from each other. And this leads very quickly to a massively parallel computation. So if all the entries are 1000, then we have 1 million inner products to compute. So this is a problem that scales very rapidly. So it's a computationally also computationally intensive operation. Here is a pictorial representation of this data parallelism. So you can imagine every one of these matrices filled with numbers. So here we have represented one of these numbers with this square, and this lines up with the ith row of the first matrix and the jth column of the second matrix. Also, the dimensions are nicely lined up. For this to be well defined, the number of columns of A must equal the number of rows of B. And the number of rows of the product is the number of rows of A. The number of columns of the product is the number of columns of B. Okay, let's now go to the compute unified device architecture. So we will launch a kernel. So the inner product will be defined in one function. It's a data parallel function. It's called a kernel. It will be called from the host, called from the CPU, but executed on the device, executed by the GPU. So that's why we have to put the keyword underscore underscore global underscore underscore before the function definition. So there is one function essentially that we are going to define, and we had a lecture on CUDA. Actually, we've seen the function already, but then it came kind of as a culture shock. The goal of this lecture is kind of to repeat this, but then within the framework of the C programmer. So again, this is massive parallelism. In a way, we encountered this earlier in the course with tasking. So tasks are logical, and we can generate many of them. Threads are actually not logical, but of course, they have some meaning, but they correspond to the instructions that are going to be mapped on the course. So in order actually to keep the GPU well occupied, we actually need a multiple of threads scheduled than we have available cores. So actually multiplying the matrix multiplication is actually an excellent candidate for this. We do not have GPUs with millions of cores, but that doesn't matter. We can efficiently schedule all these instructions. Okay, so there is the device that helps with the acceleration of the code that is executed on the host. In general, any program will have some part that doesn't have any data parallelism that needs to be executed then on the CPU by the host. The device is for data parallelism. For data parallel algorithm. We can write everything in one main program. We can also use subprograms that are included. The NVIDIA C++ compiler will separate the code that is for execution on the host, and we can specify which C and C++ compiler needs to compile this. And then there is the code that is in the files with the extension CU. That is the code for execution on the device. Here is the execution. So when we launch a program, we specify the number of blocks and we specify the number of threads per block. So this leads to a very scalable model. The blocks of grids are then processed by the streaming multiprocessor. So one block of threads consists of will be mapped onto the cores of the GPU. So we always have the kernel that is defined by a function. There are the arguments of the function. So if you look at this line, and then in between, we have the execution parameters. So the execution parameters, the number of blocks, the number of thread per blocks, they can be constants, but they can also be computed by the CPU. So there's always code that needs to take care of the data transfer. The data that is in the memory of the host needs to be transferred to the global memory of the device, and then after the computations, the mirror operation needs to happen. So the result needs to be transferred from the device onto the host. Okay, so earlier in an earlier lecture we had a 5-step process to write a CUDA program. Here we have a 5-step program for the matrix multiplication. So this is done in an environment where the memory is not managed by the system, but we have to take care ourselves of the allocation of the memories. There are the data transfers, so the input matrices have to be copied from the host to the device, and then the kernel is launched, and that will do the matrix multiplication. And then we do the transfer back from the device of the host of the output. And ultimately we free the memory on the device. If you only have one run, this doesn't really matter, but if you would run this frequently, you actually do not want to have in a situation where there is too much memory that's occupied. Okay, so let's do the plain matrix multiplication. So we will be using matrices that are stored not as rows of where we have arrays of rows, but we will have one single array that will store the matrix. So this is the linear addressing system. We start counting from 0. So you can see that at position 5 we have the first element of the second row. How do we compute the 5? Well, we have the number of elements on the previous row. So there is this offset. So the address calculation will take care of the number, will take into account the number of elements on each column, and then the row number of the element, and then the position of the element in that row. So you can see the mapping from the two-dimensional array onto the linear addressing space. And one can also compute via modulo 5 in this case. So you do the division by 5, the integer division, then you know the row, you do the remainder modulo 5, and then you know the column index. So there is a one, so here I present it as a one way going from the two-dimensional matrix to the single addressing space, but you can of course also go back. All right, C, we will generate a matrix where the matrix actually is one array, one single array of single floats, so 32-bit floats, n times m numbers here. We will compute either zeros or ones, which is very convenient for checking, or we will compute random floats. So this is a more purish C program. You see the pointer arithmetic, where we will assign to the position in the array and also incrementing after each assignment. Important that I probably should have mentioned right away. So you notice the keyword underscore underscore host underscore underscore. So that is a directive. That's a keyword to tell the NVIDIA compiler, look, this function will be executed by the central processing unit. Also the writing of the matrix. So we want to see when we test the program whether the product was actually computed correctly. Certainly if we do this for a 3, 4, 5 problem. So here you see the C code to do the printing. Okay, so now comes the important part, the definition of the kernel. So this is the function that will be executed by the device. So this is data parallel computation. So the thread, the ith thread, will compute the ith element in the result. So here you see the matrices A and B in their two-dimensional representation for the 3, 4, 5 example. We have 15 numbers that are computed. The seventh number is computed by the seventh thread, and the seventh thread corresponds to the element on the first row, second column, or actually one should see this as it's already the second row, so C1 we start to count from 0, and the seventh element is already in the third column. So we will run through all the elements of the middle in the inner product. We run through all the elements on the middle row of A for the C1, 2, and we take the middle column of B. So that's the middle element, the seventh element, the C1, 2. And that element can be computed completely independently from any other element in the output. So this is data independence. This will lead to a data parallel algorithm. So the data structure is actually determining which thread executes what statements. So it's determined by the data. The formula is there, so the threads will be launched in one-dimensional array of threads. So here for this problem, we will be launching a block of 15 threads. So 15 threads in total, but actually you can see that we will actually have more blocks. So we will have the thread identification number will actually correspond to the number of blocks will be equal to the number of rows here. So we have the block index. Let me continue. I'm explaining this not all that well now. But what I skipped over also was the reverse indication. So the matrices A and B, we have to compute from the thread index, the row index, and the column index, because we will go through all the row elements of the first matrix and to all the elements on a certain column in the second matrix. So here this is defined, so the row of C and the column of C. You see that we use the row of C to navigate through the elements of A on that same row, and we use the elements, the column of C, to navigate through the B matrix. So right on top, this is a function for which we have inserted the keyword underscore underscore global underscore underscore. So this is a function that will be executed by the device. So there are the three first parameters: the number of rows of A, number of columns of A, number of rows of B, so that's the M, and then we have the P, the number of columns of B, also the number of columns of C. Every thread has a unique identification number, so this gets mapped onto the data. So the ith thread initializes the ith entry. And actually I said this already, I think when I had the CUDA, that actually this loop is not so good, because it's going to do with every arithmetical operation, it is going to do an access to the global memory of the device. But at this stage, we actually shouldn't think about this. Let's worry about the logical correctness. So I'm using the pointer arithmetic of C. So you see that each time when we use an element of A, we do the dereferencing, and then we increment the pointer. So the P of P capital A is the position of the current element in the array A. So we go linearly through that column of A. So the elements on every row are stored in consecutive positions in the row, in the one array representation of the matrix. In the matrix B, we work in one column, so we have the column where we start. So what this means is that we skip these elements. So we start, if we have the middle column in our example of 5, so the middle column, so B had 5 columns in our example, then actually we skip the first 2 elements on the first row. So this is where we start. And then you see that each time the address is recomputed. So we compute a new value for the P capital B, where the number of elements that are skipped corresponds to the number of rows. So each time we have the number of elements on each row. So the K times P indicates the offset each time. Okay, so this is complicated, but this accurately defines the memory layout, how the matrices are actually represented in main memory. So the matrices A and B, how they are mapped onto these one-dimensional arrays. So this is somehow the virtue of C, that you can very well track what is actually happening during this computation. And this is one of our baselines, so it's not a good code, but it's a correct code. Okay, so when we run the main program, we can run it on this simple example 3, 4, 5, and the mode is 1, so we generate 0, 1 matrices, and you can verify that it is correct. So let's now go really into the main program. So we take the mode is, I'm sorry, I was saying this wrong, whether you want output or not, so that's the mode. If you do this for very large dimensions, you may not want to see everything. If there is no output, you take a fixed seed. For timing purposes, this could be interesting. Now comes the part where we allocate everything. So we have 2 memories to worry about. So we have the main memory on the CPU on the host. So I have the variables A host, B host, C host. So these are allocated with the normal C allocations. And then we have the A device, B device, and C device. You see that for each of these allocations, we are going to compute the number of bytes. So the matrix A is n by m, the B is m by p, and the C is n times p. So you see that there is kind of a accordance between the first three statements and also all the allocation statements that are done for the matrices A, B, and C. In the meantime, we generate the random matrices on the host. So we first define the A host and the B host. Okay, so then comes the um, copying. So we have the A host and the A device. We must copy from the host to the device the matrix A, also the matrix B, before we invoke the kernel. So now comes what I kind of got stuck on when I was explaining the kernel. In some sense, the index calculation was not independent on how that the kernel will be launched. So in some sense, this is a little bit, how would I say, the way you define the kernel with the mapping of the thread index onto the data, that is tied to the number of the way the threads are organized. So here we have a one-dimensional organization. We are only going to define one block of threads, and we will have n times p threads. Why n times p? Well, that's the total number of inner products that we have to compute. And we do this on the A device, B device, C device. Because why is that? Well, the A host, B host, C host are only known inside the memory of the CPU, not in the memory of the GPU. So we must then also, before that, for the very same reason, we must copy from the device to the host the result. And then as a correctness check, we print the result. Okay, so this is our first matrix multiplication in C. Why do a one-dimensional addressing if a matrix is two-dimensional? Well, you can do a two-dimensional organization where you have a grid of block dimensions where you have a one block essentially also, but now the threads inside that block are organized in a two-dimensional way. So we are also launching now n times p threads, but it's probably a little bit more natural now. Now you have to work with a row index and a column index. So that is the usage of the thread idx.x and the thread idx.y. But then one must launch the kernel using here the dim grid and the dim block as they are defined here. Also, the kernel will then change. So here is the revised kernel. So now we are using a two-dimensional thread organization that allows us to work with the I and the J. All matrices are actually still mapped onto one-dimensional arrays. So you see the computation now of this L, the I times the number of columns of C plus the column index. So that determines also the position now. But now this instruction is executed by the thread I, j. So there is not so much a direct combination anymore. So there is not anymore a direct correspondence between the data elements. So the location of the data element is at L. So that's the Lth position in that one array representation of the matrix C. And then the thread is the ijth thread. So the name of the thread, it has a first name and it has a last name, a row and a column index. For the inner product, we still do the same pointer logic, although I'm already using now here the bracketing notation for C and for A. For the B matrix, I still had this address computation, although it could also have been a little bit simpler. Okay, so this is the second kernel. So there are many ways how to define this. So this is still up for testing without too much an eye for performance. All right, let's think about performance then. So I prepared the slides a while ago. This is for a Kepler computer with the K20C card in there. Perf is a tool, a performance analysis tool for Linux, and it will allow us to compute the number of floating point operations in a run. You could actually also have some helper functions do this for you. So if you cannot use this performance analysis tool, you can essentially compute with the arithmetical operations. You can compute the number of operations that are done. You have to know for your processor the number of instructions that you want to time. So you have the doubles that are executed. We are interested in performance, so all the executables are compiled with an optimization flag. Okay, so here it is. So this is our very basic matrix multiplication. I twiddled with the parameters, so instead of 3, 4, 5, I had 745, and I wiggled with this till I have 1 second that was passed. So then I can compute, as you can kind of see that I have 2.4 billion or close to 2.5 billion operations in a second. And this allows me to compute then the number of gigaflops. So the 2 to the power 30 is used for the billion. So we are so the numbers that are reported are in this decimal notation, are in the binary notation. So the giga is 2 to the power 30. That's what I should have said from the beginning. So you can see that the processor speed kind of corresponds to the peak performance on this one CPU core. Of course, Kepler is a 32-core machine, and it's a hopeless, it's not a fair comparison actually. But we will still have a lecture on numerical linear algebra. We can still make up for that. All right, so then the Kepler card. So you can also do the performance analysis for 745. Now you see that actually if I want to keep 1 second, if I want to keep the card for 1 second busy, then actually it's not such a good computation. So you actually see also the wall clock that is done. So the wall clock shows that actually the card was busy for 462, or actually the total system time, which also includes the time on the GPU, is also already increasing. Okay, but to do this also for a larger problem, I took dimensions 4000, and then you see that it takes 171 seconds. So we have a larger problem um, for which the CPU takes 171 seconds, so already close to 3 minutes. With the GPU, this gets 1 second. So you can see, of course, again, the comparison is not fair. One core on a multi-core processor against the Kepler, which has actually teraflop performance, a theoretical peak performance. This is both good and both bad. So you see the bottom line is here that I get to a performance of 246 gigaflops, which is not really fully utilizing the GPU. But however, I'm actually running this on a very basic implementation still. So I'm probably also using only one block, which also is a severe limitation on the parallelism, on the total number of instructions that can be run in parallel. But still, with this very basic implementation, very plain implementation, we actually get a huge speed up. So the speed up is indeed double-digit speed ups. It is a naive computation. Still, we will improve on this in later lectures. Okay, so running on the Pascal. So that's the current GPU that we are using now. You can see that even here we get close to the teraflop. So we actually we get 700 gigaflop, which is not bad. And I say here matrix multiplication is an n to the power 2 multiplication. Actually, this is not true. So this is an embarrassing bug still. So it's an n to the power 3 multiplication. We expect the time to be multiplied by 8. So not really quadruple. So what this actually shows that for larger and larger dimensions, the problem actually scales quite well. It doesn't get multiplied by 8. Okay, Julia. So this is an ending, which is a little bit perhaps anticlimactic. Just also to make the point, if you really need to multiply two matrices, then you better use the libraries that come with the software development kit. So here is the very high level implementation and program in CUDA using the Julia version of it. So you have the data on the host. So here I have a 1000 by 1024 by 1024. So I'm doing more than 1 million inner products here. So I create a matrix, a random matrix on the host. So A underscore H, that's the one on the host. And then actually the corresponding one is A underscore D. And you do the allocation, the copying simply with this CU array. So there are in some sense, this is great, but if you only see this and only see this for the very first time, then it takes a lot of explanation. So what we have done so far with the C code is very instructive to see what really is happening. So you can see also here, if we do the benchmark timing, and one should do the timing with the benchmark tools, so using this macro btime, then you see that the time, so if you run this run these instructions, I ran it on the command prompt, and what you see on the command prompt, notice here that the semicolons are quite useful. So the semicolons suppress the output. So we do not really want to see 1 million floating point numbers. So, but the main point is that the time goes from 4 milliseconds to 13 microseconds. So you have really one magnitude that is, and matrix multiplications occur many times. So you have a really great speed up. I also did this on a high-end Windows laptop with a NVIDIA graphics card, the RTX 2080, and I got similar results. So very little code, very little effort, but huge benefit. So I will end with plain matrix multiplication, now implemented with a two-dimensional thread organization. So I will run this. So I run it for here. I print the matrices at the end. So this is done with 4x4 matrices. You can also do this also with 1 million numbers, but the print, you should leave it off then. So the main point of this slide is to indicate the high level definition of the matrix multiplication. So if you're not so much familiar with the syntax in Julia, then this might not help you all that much. But if Julia is your first language, and if you have to teach this to people who are first programmers, then this keeps the logic of the matrix multiplication. You see the inner product shown with a two-dimensional array. So the macro inbounds tells the compiler not to check for the ranges. So we know what we are doing. So we have this two-dimensional thread organization. So this is the data parallelism. So every thread has the double name, first name row, second name column. And now this corresponds kind of neatly with the indexing. Of course, also in C, we could have done this if we were using the square index notation. Okay, so what this will do, this will check the correctness. So what the purpose of the script is to indicate how you launch a two-dimensional thread block. So we, here in this slide, the dimension is 4, so we do 16 inner product. So we launch one thread block of 16 threads with this macro CUDA. And this will print the same matrix twice if everything goes well. So we first compute it on the host and then we compute it on the device. You see the initializations, the making of the random matrices, and the array is going to take care both of the allocations and the copies. So the nice thing is that this environment takes care of the memory transforms. So the C_D is immediately available to the programmer without having to invoke device to memory copy. Like we did in CUDA, we had to do this in CUDA, and we also had to do this in C code. So Julia allows to work at the highest level. So that was the previous slide. This slide is kind of in between. So you still get to see the logic of the matrix multiplication, but you get to also you get to define the data parallelism. Okay, so that was our first lecture on matrix multiplication, mainly to examine the very basic implementation. So in the next two lectures, we will see improved versions. So the data layout is definitely not optimal. So the exercises in this lecture invite you to play with the code. One can also make the C code a lot more readable and a lot more natural. So in some sense, the first presentation of the code was perhaps a little bit too low level. Okay, so I hope this lecture was interesting. And in the next two lectures, we will see on how this gets improved. So this was first rather straightforward consideration and treatment of this problem.